Good morning. Let us see couple of structures based on VSEPR theory. We have seen BrF3 molecule, its valence electron you can calculate 7 electron plus 3 into 7, okay, then it gives 28 valence electrons, and then you can arrange the electrons around the boron atom, bromine atom as a central atom. So, you can have fluorine, 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 fluorine. So, there are 6 electron pairs, 6 electrons were used. So, minus 6 remaining 22 electrons, then we put the electron here, here, here and here, here, okay, and then so there are 18 electrons are gone. So, you have a 4 electrons, that 4 electrons should be given as pairs on the central atom. So, there are, so in so if you look at the number of pairs of electrons 1, 2, 3, 4, 5, there are 5 electron pairs. So, if there are 5 electron pairs, then the shape is a trigonal bipyramidal. So, you have a bromine, and then you have here, and then you have here. Trigonal bipyramidal. The shape of the molecule is a bend T shape, because we put that because these two lone pairs repel each other. So, lone pair repulsion is the highest one. So, it pushes the bonding electron pairs in such a way that the angle is not 90 degree. The angle between this angle is not 90 degree, it is slightly bent. So, it is about 86 degree. So, because of the repulsion, strong repulsion between the two lone pairs, it pushes the bonding electron pairs little bit down. So, the shape becomes a bent T shape, because it looks like a shape. Then another molecule is the ICl2 minus. For that, you can calculate the valence electrons. Iodine valence electron is 7 plus 2 into 7, valence electron chlorine is 7 plus 1, in total you have 22 valence electrons. 22 valence electrons. So, you can draw approximately shape of the molecule. Two chlorines here, there are 4 electrons consumed, the remaining is 18 electrons, and then 18 electrons you can give as pairs like that, and then minus 12 are gone, remaining 6, then you have to give here and here. There. So, now the total number of valence electron will be matching. So, this structure has 2 bonding pairs and 2 lone pairs, 3 lone pairs, because 1, 2, 3 lone pairs, 2 bonding pairs. So, in total there are 5 electron pairs. That means the expected geometry for this molecule is the trigonal bipyramidal, and then you can put the lone pairs in the equatorial plane, iodine, and you can have the lone pair here and here and here, and then put the chlorine here and in the axial position, so that the structure is minimized and the shape of the molecule is linear. The shape of the molecule is linear. Okay, so because we should not include lone pairs positions to tell the shape of the molecule. So, it's a linear in shape, called valence bond theory. So, that this theory was developed by Linus Pauling. This theory is based on the Lewis ideas of electron pair is used in forming a bond. So, the valence bond theory is based on Lewis ideas of electron pair bond, which was developed by Linus Pauling. So, this theory is the bond formation using valence electrons. So, it is called valence bond theory. Why do we need this theory? There are some problems with previous theories that we have seen. For example, if you look at Lewis dot structure, it does not tell about the angle between the three atoms. Okay, you cannot find out, you cannot determine what is the angle between atoms. Similarly, so we cannot, so as a result we cannot get the shape from the Lewis dot structure. Then we have seen Valence bond theory, so called VSEPR theory. Under that theory, we discussed shape of the molecule based on repulsion between the lone pair, electron pair and electron pair repulsions. So, though based on those repulsions, shape of the electron pairs are arranged and shape can be determined based on the position of the atoms. So, but it does not give, VSEPR theory does not give explanation or describing in details about the shape of the molecules. So, there is another theory needed for explaining the shape of the molecule. One of the theories is the valence bond theories, another one is the molecular orbital theory, that we will see later on. Let us see valence bond theory. So, this theory is basically requires overlap of the orbitals. You have studied each atom has orbitals and with containing some electrons. So, the basic idea behind this valence bond theory is the sharing of electrons. Electrons are shared by overlap of the atomic orbitals. Okay, so under this orbitals, atomic orbitals overlapped. Atomic orbitals are overlapped and electrons are shared. Between atoms. So, under this theory, a pair of electron is required to form a one bond. Okay. It can also, there can be more than one pair of electrons between two atoms. Accordingly, the bond order will increase. So, at least one pair of electrons are between two atoms needed. So, this theory is based on overlap of the atomic orbitals. So, as we have seen before, you have a hydrogen atom, okay, containing 1s orbital, which is 1s1, and then combining with another hydrogen atom has 1s orbital containing 1 electron to give a hydrogen molecule. Okay. So, that is formed by the overlap of the 1s orbital, this is 1s orbital. Okay. This is the 1s orbital of the another hydrogen atom. Okay. That 1s orbital overlap with 1s orbital of another hydrogen atom to form a hydrogen molecule. Now, you see here the two orbitals are written in this way such that there is a overlap of the orbital. This is the overlapped region of the orbital. So, this okay. So, this portion is called overlapped region. So, because of the overlap of the atomic orbitals, bonds are formed. So, it has one electron and it has 1 electron. So, there are 2 electrons between the 2 hydrogen atoms. So, as this bond formation happens, as we discussed before, that you have 2 hydrogen atoms which are far away. There are 2 hydrogen atoms which are far away. When they are like that, there is no interaction between the 2 hydrogen atoms. As they get closer and closer, okay, they start interacting each other, okay, and then energy decreases and then reaches a minimum value, okay, at which the energy is the lowest, okay, and the bond is formed, which is described by this potential energy diagram. So, energy here it is a 0. Okay. So, this is positive energy, here is a negative energy. So, you are starting with 2 hydrogen atom, okay, another 2 hydrogen atom here, Okay. So, here there is no HA, okay, let us say HA, this is HB, okay, 1s orbital, 1s orbital, between two hydrogen atom there is no interactions, potential energy is 0. So, as they get closer the energy decreases, okay. So, they reaches minimum and then increases. Okay. So, as they get closer in, okay, they attract each other, that is why energy is decreasing, becoming negative negative and then reaches the minimum. Okay. So, this is internuclear distance, okay, internuclear distance. Okay. So, this is increases. So, from here this is 0 to some positive value increases. So, it reaches minimum at which this is the energy of the molecule, this is the distance between the two hydrogen atom. So, at this distance a bond is formed and energy is released. So, how much energy released? The difference between this and this is released. So, at this stage energy is higher, here the energy is lower because a bond is formed. When bond is formed it becomes more stable and then that much from here to here, okay, from the difference between this level and this level, energy level, energy is released. As a result a stable molecule is formed. Okay. So, in this way a bond formation is explained in valence bond theory. Now, so you have not only you have 1s orbital, you have also have p orbitals and then you have d orbital, f orbitals. We are not going to consider overlap of the d orbital, f orbital, we are going to consider only s and p orbitals. So, which are the orbitals can overlap, what are the types of overlap which can lead to a bonding. So, for that you should be familiar with orbitals. What is orbital? Okay. So, you have a 1s, okay. For hydrogen it has 1s orbital and there is one electron here, okay. This is center of the nucleus, okay, and you have 1 electrons, okay. So, this is a 1s orbital. For hydrogen atom the 1s orbital is spherical. Actually, what is orbital? Orbital is a region around the nucleus where finding the electron is very high. The probability of finding the electron in that region is very high, that is called orbitals. So, you take a orbital means finding the electron, probability of finding the electron in that region is greatest. Okay. So, then that orbital is overlapping or mixing with another orbital, okay. Then there is a bond formation. For bond formation electrons are needed, okay. So, that nuclei are attracting them. So, this is a 1s orbital shape. If you take a shape of the 1 orbital, spherical shape, if you take a p orbital, there are 3 types of p orbital. So, if you say this is a, okay, this is x, this is y, this is z, there is a orbital along the x axis, there is a orbital along the y axis, there is a orbital along the z axis. So, there are 3 p orbitals, that is px orbital, py orbital, pz orbitals are there. All of them can be used for bond formations. So, which orbital can overlap with which orbital? That is what we have to look at it. So, when you look at that, we can also tell from the nature of the overlap whether there can be a bonding or not. So, that is why there is another concept called the overlap, criterion of bond strength. Overlap criterion of bond strength. So, that means there is a relationship between the nature of the overlap and the bond strength. Okay. So, because overlap is important to have a stronger bond, the higher the overlap the stronger the bond. That means you have a 1s orbital, for example, plus 1s orbital can give a overlapped bonding orbital. Suppose this is this much is the overlap. Suppose if you have a overlap, it is also possible to have overlap this much. So, the overlap here is very less. You can also have situation like this, little bit higher than this, okay, higher than this. So, you can have, so among these three, which overlap will give the higher bond energy, which will give strong bond. I would say it is found that this type of overlap, because the overlap is higher, the mixing of the orbital is higher, that will give the stronger bond compared to other two where the overlap is less. So, that is why the higher the overlap, the stronger the bond. That means, when there is a higher overlap, when there is a more overlap, there is a buildup of electrons between the two nuclei. Okay. As a result, when there is a buildup of electrons between the two nucleus, okay, between two, there is one nucleus, there is another nucleus, and you build up electron between them. So, as okay, electrons are shielding the two nucleus. Okay. So, there is a less repulsion, repulsion is avoided between two nuclei. At the same time, attraction between electron and nucleus is increased when there is a buildup of electrons between the two nucleus. So, that will happen if there is a very good overlap. So, overlap is related to the bond strength, higher the overlap, higher the bond strength. So, that is so one can tell from the nature of the overlap whether there is a bond or not. So, let us see what are the ways in which orbitals can overlap, okay, which will lead to a bonding, which will lead to a bonding. That means, there is a buildup of electron density between the two nuclei, and there are some overlaps which will lead to reduction in electron density between two nuclei, and as a result overlap integral or overlap is negative. Okay. And then there are overlaps where the overlap is 0. Let us see what are they. Okay. So, let us see, this is the z axis and you have a pz orbital, this is positive, this is negative. Whenever you draw a orbital, the sign of the wave function should be given. So, this is positive, this is positive, okay, positive, this is positive, okay, this is the positive sign, okay, this the negative or positive symbol refer to the sign of the wave function. Okay. So, negative or positive refer to the sign of the wave function. What is wave function? That we are not going to see now here, you will be studying in higher classes. So, for time being you keep it. Okay. So, this is a wave function which is used, a wave function is a mathematical equation. Let me simply describe them. Mathematical function used to describe the orbitals. So, orbitals were actually in fact a graph. Okay. So, this is not the picture of the pz orbital, remember. Okay. So, it has a shape like that, but it is a plot of mathematical function. Orbitals are plot of mathematical functions. As you plot x, y, okay, here also the orbitals, this type of shape was obtained by plotting wave functions. So, you could describe orbital using wave functions. So, whenever you are drawing an orbital, it is important to give the sign of the wave function there. So, if you take a p orbital, pz orbital, let us say this is positive, this is negative. Now, it could overlap with s orbital. For example, s orbital is this plus. Okay, this is a sign of the wave function of the s orbital is everywhere, 1s orbital is positive everywhere. So, it is spherical symmetry, okay, spherical in shape. So, everywhere it is positive. So, it can overlap with this orbital in any direction, because everywhere it is positive. But on the other hand, if you take a pz orbital, it has a positive wave function here, here it is a negative. So, to have a bonding situation, or to have a overlap which will lead to a bonding, then it has to overlap in this way only. So, this is one atom containing, for example, hydrogen 1s orbital, and then there is another atom having a pz orbital. They approach each other to form a bond. To form a bond, it is very important to understand that. So, you have atom A, you have atom B, then there is a axis. There is a these two atoms should come in the same line, or in the same axis. If they want to use its own orbital which is lying in this axis, to have a maximum overlap, these two atoms should be collinear with the orbitals. For example, atom, this is atom A, this is atom A uses its pz orbital, then the s orbital can overlap anyway, because it is more symmetrical, should come in the z axis only. To have a maximum overlap, another atom should come in the same axis, otherwise the overlap will be very less. So, it should come in the same line. So, you can see that. So, this atom is approaching this atom, or both of them approaching each other to form a bond, and that can happen if the overlap is good. So, what overlap is good? Which overlap is good? If you have this is a p z orbital, negative, positive, and then you have a 1s orbital. It is everywhere it is positive. This is p z minus 1s orbital. 1s orbital of the hydrogen atom. Now, there is a positive overlap. Now, you can see that I put two orbitals together where the sign of the both orbitals is positive. So, sign of this orbital is positive, sign of this lobe of the pz orbital is positive, but this lobe sign is negative. So, positive positive. When you have two lobes having sign of same sign, having the same sign, then when they overlap, that type of overlap will give you bonding. So, here the overlap is positive. The overlap is is greater than 0, which is greater than. So, that means there can be a bond formation. There can be a bond formation between this atom and this atom, because the overlap is greater than 0. Suppose if you draw the same one in this way, you have positive, this is negative, I put negative, this is positive, and then you have another atom which is 1s orbital, this is pz orbital. They approach each other to each other. As a result, when they overlap, assume that they are overlapping, then what will happen? If you draw the diagram in this way, this is a negative, this is positive, this is positive. So, this is a pz minus 1s orbital. Here the overlap is less than 0, this is negative, it is overlap is less than 0, it is negative. So, this is a positive overlap, this is positive overlap, this is negative overlap. Which overlap will give you bonding? Only positive overlap will give you bonding, will give a bond formation between two atoms. Negative overlap will give you a situation where there is a reduction in electron density between the two nuclei. So, as a result, nucleus repulsion will be there, and there will be no bond formation in this case, because overlap integral or overlap is less than 0. Why it is less than 0? The sign is opposite. So, these two orbitals are not having the same sign of the wave function. Here the sign of the wave function negative, here the sign of the wave function is positive. When you put them together, they cannot lead to a bonding. So, the bonding overlap is less than, it becomes negative. So, those positive negative can be calculated by quantum mechanics. Without looking at calculations, one can tell from the sign of the wave functions, okay, which are overlapped. You can tell which overlap is bonding for bonding, which overlap is for will lead to a overlap of negative. So, only positive overlap will give a bonding situation. This will not give a bonding situation. So, so far we have seen overlap of the s orbital and p z orbitals. Now, let us see overlap of the p orbitals. This is a z axis, you have a 1 p z orbital. This is positive, this is positive. I am sorry, this is negative, positive, negative, because sign of the wave function changes after the this nodal plane, as you studied before. Now, you can have another orbital overlapped with this one. Okay. This is positive, this is negative. Now, this sign of the wave function for this orbital is positive, this is also positive. Here the overlap is okay, positive, overlap is greater than 0. If you draw this diagram in this way, this is negative, this is positive, this is negative, this opposite is positive. So, here the overlap is okay, so negative, less than 0, it is less than 0, because okay, so this region, okay, is a positive negative overlaps. So, the positive lobe of this orbital is overlapping with the negative lobe of this orbital. So, as a result, overlap is less than 0. Here both are positive, such a overlap will give a bonding situation. Okay. So, that is why overlap is greater than 0. Now, p orbital can also combine, can also overlap in this way. Okay, this is a x axis, this is z axis, this is p x, this is another p x orbital, or you can have or you can also have p y orbital. So, this is a positive, positive, negative, negative. There is, so here the overlap is positive. Okay, overlap is greater than. So, that is a positive overlap. Okay. If you draw the same this diagram in this way, positive, negative, negative, positive, see that here the overlap is less than 0, so negative. So, negative. Okay. So, this is not for bonding, this is for bonding. So, p z orbital combining with another p z orbital, because they are coming in the same axis. Similarly, p x orbital or p y orbital can combine with p x p y orbital of the another atom to give a bonding overlap. It can give overlap of negative overlap. Now, you can also describe which. So, now we have seen overlap integral or overlap of greater than 0, less than 0, and which are the situations are for 0 overlap. If you take s orbital, this is a b, okay, one axis, and then you draw a okay, s orbital, which is combining with okay, p x or p y orbital. Here this is 1s orbital or s orbital. Now, here okay, now here overlap equal to 0. Now, because say this is a positive of the positive, this is negative, for s orbital it is positive everywhere. So, here positive, so there is a overlap is greater than 0. If you come here is a positive, here is a negative. So, here the overlap is negative. So, positive overlap, negative overlap, they cancel each other. So, that overlap equal to 0 in this. So, this way atoms cannot form a bond. Okay. So, this is the new center of the nucleus. of one atom. This is the center of the nucleus of another atom. They approach each other to form a bond. So, if their orbitals are oriented in this way, for s orbital everywhere it is same. For px orbital, if it is oriented in this way, then it will lead to a overlap of 0 value. Okay. Then you can also have another situation. So, this is a x, this is a z axis. So, this is this orbital is for example, this is positive, negative, negative, positive. So, this one is the y axis. So, z axis, y axis, x axis. So, we are trying to combine px and px orbital of one atom, py orbital of another atom. You know that px, py, pz orbital are orthogonal to each other. So, the angle is 90 degrees. So, that is orthogonal. So, this is in on x axis, this orbital on the y axis. When they want to, when you put them together, okay, to form, then you will have like this type of situation. This situation here the overlap is equal to 0. Okay. So, these are the types of overlap. What we have seen so far is the types of overlap for bonding, okay, and for bonding, and when the overlap is less than 0, that is negative, there is no bonding, the overlap can be 0. So, overlap can be 0, it can be positive, negative, and then the magnitude, you have to remember that how much it can overlap, that depends on the nature of the orbital and the internuclear distance. As the internuclear distance between two atoms decreases, the overlap will be more. At the same time, when it approaches, when they approach each other too much closer, there is a repulsion. So, also the shape of the size of the orbital, when for example, you take a smaller atom, you take a larger atom. Larger atom means it has a okay, larger orbitals. Smaller atom, small orbital. When they overlap, what will happen is the overlap cannot be effective. It will lead to a negative overlap, because suppose you have for example, you have a 1s orbital. Okay, this is the center of the nucleus of one atom A, and then you are bringing another atom has a p orbital, pz orbital for example. And then suppose if it is overlap too much, okay, suppose this is okay, this is a positive, positive, this is good. Suppose if you overlap in this way, okay, in this way positive. So, there is a positive, this is negative. So, it will lead to a negative overlap. So, it should not be. So, the overlap magnitude of the overlap depends on the internuclear distance and shape of the orbitals, Those details we are not worrying much right now. What we wanted to emphasize here is the overlap of the orbital. What are the types of overlap, overlaps of orbitals for bonding. Now, with this knowledge of overlap is important to understand the bonding under the valence bond theory. Okay. Now, we are going to a very important concept, that how the bonds are formed under valence bond theory. For example, if you take a hydrogen atom has one electron combining with chlorine, it has a one unpaired electron can give, okay. So, hydrogen Cl like that. Okay. So, a pair of electron is between hydrogen atom and chlorine atom. You have single bond is formed, that is called covalent bond or sigma bond. Okay. Similarly, if you take a nitrogen, 3 unpaired electrons are there. So, one lone pair can combine with another nitrogen atom having a 3 unpaired electrons to give 3 bonds between the 2 nitrogen atom. 3 nitrogen. So, there is this is equal to, which is equal to, okay, 3 like this, like. So, 3 bonds are formed, 3 covalent bonds are formed between 2 nitrogen atom. Okay. Now, so because so the bonds are formed because each atom contains one unpaired electrons. Okay, so that many number of bonds are formed here, there is no problem here. Similarly, if you take a okay, so hydrochloride that I explained here now. Now, if you take a carbon, okay, for example, methane, okay, there are 4 bonds are formed, but if you look at the electronic configuration of carbon is 1s2, 2s2, 2p2. Okay, so its energy level I can draw in this way. The valence electron, this is the valence electron. So, this is a 2s orbital containing 2 electron, and then you have a so this is the energy. Okay, this is a 2p orbital contain 2 unpaired electron here and here. One of the p orbitals is free. Now, if you look at that way, as you have seen here, it has one unpaired electron, combined to form a covalent bond. Same way, if you look at the electronic configuration of carbon atom, it has 2 unpaired electrons. So, that means it can combine with 2 hydrogen atom. Okay, okay, let us say this way itself 2. So, combine with 2 hydrogen atom, okay, which has 1 electrons, and you can have carbon, okay, like this. Okay, you can form, but it is not the case. It is not forming in this way. So, you will have carbon forming CH2 only, which will be a more stable if you go by this way. In reality, this is very unstable molecule. However, it exists with different R group. Replace hydrogen by R group, you can stabilize that we are not studying here. So, this is not the actual situation. What we have here, CH4, okay, 4 hydrogens atoms are bonded to 1 carbon atom. How is it possible? Why I am asking is that carbon contains only 2 unpaired electrons. How it can go to a state containing 4 unpaired electrons, so that 4 bonds are formed? Why we need 4 bond? Why we need to have 4 unpaired electrons? Because there is, okay, a pair of electron is needed to form a bond. So, one atom gives 1 electron, another atom gives another electron. So, a pair is formed between that hydrogen, between 2 atoms, a bond is formed. So, carbon has to have 4 unpaired electrons to have a 4 bonds. How is it possible? So, you have to do or introduce a concept, another concept. That concept is called hybridization concept. Hybridization or mixing of orbitals, of atomic orbital, hybridization of atomic orbitals. So, let us see how to do a hybridization. As I said before, so here you have a 1s orbital for carbon, 1s orbital containing 2 electrons, and then you have 2p orbital containing 2 unpaired electrons. Then you have to promote one of the electrons from here to here. So, promotion electron. Why do you need to promote electrons? To have unpaired electron, maximum unpaired electrons. Here is the okay, so 1 electron, because one of them is gone here. Okay, so you can have like this state. When you promote 1s orbital, okay, sorry, this is a 2s orbital electron to the 2p orbital, because it has 1 vacant orbital. Okay, so we need to put 1 electron here, that is promoting electron from 2s level to a 2p level, so that the carbon will have 4 unpaired electron. Why do you need 4 unpaired electron? To explain the CH4, to explain CH4. So, it is like that. Okay, so there are 4 covalent bonds around the carbon atom. So, that means the carbon should have 4 unpaired electrons. So, that is why we imagine that one of the electrons went to the 2p orbital and forming 4 unpaired electrons. Okay. Then the carbon can form a 4 bonds. but you remember that this is one, okay, 2s orbital, this is a 2p orbital, 2p orbital. So, let us say this is a px orbital, this is py orbital, this is as pz orbital. Now, let us draw a diagram. This is, let us say this is x, this is y, this is z axis. Okay, this is a carbon, okay, a hydrogen atom. So, you have a 3 p orbital, 1 s orbital. Okay. So, that means these 3 p orbital can combine with 3 hydrogen atoms, each having 1 electrons. So, you put a hydrogen atom here, this is hydrogen atom, for example 1 hydrogen atom, you put another hydrogen atom here, you put another hydrogen atom here. Okay. So, 3 bonds, 3 covalent bonds are formed using 3 pz orbital. So, this is a carbon, okay, 2p y orbital plus, okay, hydrogen 1s orbital. So, okay, a bond is formed, a bond is formed. Similarly, this bond is formed, this bond between this carbon and hydrogen is formed using carbon 2 p x orbital plus hydrogen 1s orbital. Similarly, this bond is formed using carbon 2 p z orbital plus hydrogen 1s orbital. Okay. So, 3 bonds are formed. The fourth bond could form, okay, using 2s orbital present on the carbon atom. So, which would be here, which would be here. Okay. This is a hydrogen atom. So, this is a carbon 2s orbital combining with the hydrogen 1s orbital. Now, see that 3 bonds are formed using 3 p orbitals, another bond is formed using, okay, carbon 2s orbital. Okay. Now, you know that it is a geometry or shape of the molecule is a tetrahedral, angle between these 2 hydrogen atom, angle is here, this angle is 109.5 degree. Okay. But if you look at the angle here, the angle between these 2 axes is 90 degree, or here it is a 90 degree, but here it is around 125 degree. So, in reality, in methane molecule, the angle is 109.5 everywhere, any angle you take, it will be the same value. But in this way, okay, if you go in this way of bond formation, you would end up with molecule having certain angles 90 degree, certain angle 120 degree, which is not the case. Okay. In addition, the bond, okay, the bond formed between the carbon px orbital and 1s orbital is different from the bond formed between the carbon 2s orbital and hydrogen 1s orbital. Okay. But if you look at that, the bond energy or energy of each bond here is the same, but the energy of each bond is not same, it is different. So, this is not the way by which the bond is formed for CH4. Then what is happening? These, okay, then what to do? Then we have to introduce a concept called hybridization. Hybridization means mixing of atomic orbital. This p orbital mixes with s orbital. Okay, that is why. Okay, so once this is formed, this state is not ready for bond formation. This state is not, this state. Okay, this state is not ready for bond formation. Okay. Then it undergoes process called hybridization. Then, so you have a s orbital, 2s orbital, 1 electron, and then 2p orbital, okay, containing 1 electron, 2p orbital. Then it undergoes hybridization, hybridize, and giving 4 equivalent hybridized orbitals containing 1 electron each. Okay. This is called sp3 hybrid orbitals. sp3 because s orbital mixed with p orbital. How many p orbital? 3 p orbital. That is why sp3 hybridized orbital, sp3 hybrid orbitals. So, those orbitals, what is the difference between this orbital and this orbital? So, you can see the number of atomic orbital which are hybridized equal to the number of hybridized orbitals, same 4 atomic orbital combined to give 4 hybridized atomic orbitals. Okay. Now, when you look at after hybridization, energy of these orbitals are same, they have the same value of energy, and then when they hybridized, they look like this. A carbon, okay, you have carbon and you have a lobe, okay, and then there is a small lobe, and then there is a large lobe, opposite there is a small lobe, okay, there is a big lobe, and then there is another big lobe, there is a small lobe. This sign is positive, this is negative. Okay. Similarly, this is positive, this is negative, this is a positive, this is negative, this is positive, this is negative. So, atomic orbitals were combined to give a hybridized orbitals. Okay. After hybridization, you can see that lobe of the hybridized orbitals are larger compared to the atomic orbitals. Okay. So, when the lobe is larger, okay, so you have a lobe of this big, okay, compared to atomic orbital of like this. Okay. So, orbitals having this much lobe is good for overlap, this is good for bond formation, because the lobe is greater. Here when the lobe of the orbital is bigger, it can overlap much better way, or the overlap will be much positive, more positive compared to our atomic orbital having overlap of this size. So, that is why hybridized orbitals are better for overlapping and hence better for bond formations. So, once after formation of sp, so these are the sp3 hybridized orbital. So, what is that? There are 4 atomic orbital combined to give 4 hybridized orbital, and they have equal energy. Okay. sp3 hybridized orbital, hybrids, equal energy, they have equal energy, each contains 1 electrons, and their lobes are oriented, okay, lobes are oriented along towards particular directions, that determines the shape of the molecule. In this case, for carbon, these lobes, okay, lobes are pointed toward corners of a tetrahedron. So, when they combine with the hydrogen, a tetrahedral molecule is formed. So, you can draw here a hydrogen atom, okay, combining with this is hydrogen atom. The another hydrogen atom, you put hydrogen atom here, and put another hydrogen atom here, you put another hydrogen atom here. Okay. So, hydrogen atom here, hydrogen atom here is a positive. Okay. Here the sign of the wave function is positive everywhere for hydrogen atom, for hydrogen 1s orbital. So, that will give a carbon like this. Tetrahedral shape. That is the reason it has, okay, the angle of 10 degree and the bond strength is same. Okay. 4 bonds are formed by use of 4 hybridized sp3 orbitals, and okay, those orbitals are equal energy and contains 1 electron each, and okay, when bonds are formed, okay, they give particular shape to the molecules. In case of carbon, the shape of the molecule is a tetrahedral. So, that is how bonds are formed under the valence bond theory method. Basically, what we have seen is the overlap of the atomic orbitals. Okay, when okay, so on top of that, we have seen promotion of electrons to the higher lying orbital, and then hybridization between the orbitals, giving a hybridized orbital, okay, and then bond formation leading to a shape of the molecule. Okay. So, now let us see a simple case of bond formation between s orbital, okay, a simple molecule such as beryllium Cl2 or beryllium for example Cl2 or Br2 or beryllium dimethyl. Okay. So, now you know the what is the electronic configuration of beryllium, it is 1s2 2s2, 1s2 2s2. Okay. So, this is the electronic configuration of carbon atom, and as you know that, so this is a 2s orbital of the beryllium and contains no unpaired electrons. But how does it possible for beryllium to form 2 bonds with 2 chlorine atoms? Okay. So, that means that we can understand, that we can explain in this way. Okay. You have a empty p orbital lying higher in energy. Okay. There is 2p orbital. So, first job is promotion of electron, promotion of electron. Okay. That leads to a situation like this. This is a 2p orbital, this is 2s orbital. Now, you have 2 orbitals containing 1 electrons each. Now, it has to undergo hybridization. To give 2 equivalent hybridized orbital containing 1 electron each. So, this is called a sp hybridized orbital. Hybridized orbital or diagonal orbitals. Diagonal hybridized orbitals. How do they look like? We can draw that in this way. Here z axis. Okay. Here the 2p orbital is z lying along the z axis. So, this is a z axis, this is a p, z axis positive, this is negative, combining with s orbital, 1s okay, combining with 2s orbital of the same atom. So, you have a 2s orbital, this is a 2pz orbital, 2pz orbital, this is a 2s orbital. Okay. This is positive sign, it has positive sign everywhere and can give 2 hybridized orbital of this type. Plus this is the center of the nucleus, another one of this type. See, a large lobe and small lobe, this one is positive, this is negative. So, which we can write together a beryllium atom, and there is a large lobe and there is another large lobe. Okay, there is a small lobe here, there is small lobe here, positive. So, beryllium atom is ready for bond formation. So, then the 2 chlorine atoms can come closer to this one, they have one unpaired electron and can form a bond between them. Okay. So, the p orbital of the chlorine atom can overlap here. Okay. So, for example, in this way. Okay. So, this is a z axis. So, this is z axis. So, z axis. So, this is a z axis. So, there is another. So, because this is a z axis. So, this is a beryllium 2 chlorines like this. So, because these are the sp hybridized orbital, okay, sp hybridized orbital which their lobes are opposite each other. So, this is the center of the atom and you have a large lobe here and then there is another lobe, okay, in the opposite direction. So, angle between them is 180, it is 180 angle between the 2 orbitals. So, here the angle is 180 degree and they are, okay, projected opposite each other. So, and contains 1 electron, there is 1 electron here which is ready for bond formation with another atom having another 1 unpaired electron. So, you have a this one is the pz orbital of, okay, of chlorine which contains 1 electrons which can combine with this sp hybridized orbital to form a covalent bond, a sigma bond or covalent bond between beryllium atom and chlorine atom. Similarly, in this direction also. So, this is called a sp hybridization. So, the hybridized orbital, after hybridization, it is important to understand that what is a percentage of s orbital in the hybridized orbital. What is the percentage of p orbital in this hybridized orbital? They are equal, okay, because 2 orbital combine to give 2 hybridized orbital, okay, then its character is divided. So, because 2 orbitals involved, so it has a 50% s orbital, s character, okay, 50% s and then 50% p orbitals, okay, because 2 atomic orbitals are combined. So, you have 50% each. On the other hand, we have seen sp3 hybridization for methane. What is the percentage of s character for this hybridized orbital? It is 1/3. So, this hybridized orbital for carbon, okay, so is positive everywhere, okay, it has some, okay, 25%, okay, or some, okay, it has a 25% of s and then 75% of p character, or 1/4 of s character and 3/4 of p character for each hybridized orbitals, and that is why they are having equal energy. So, that way bonds are formed. So, you could understand here very clearly that bonds are formed by overlap of the atomic orbitals. If there is no suitable atomic orbitals available, then atomic orbital combine to give hybridized orbital, to give required number of hybridized orbital, and then bond formation takes place. Now, another molecule which we can see is the third group elements, boron, okay, it can form boron trifluoride of this type, okay. So, boron electronic configuration is you can write that 1s2, 2p 2s2, sorry, 2s2, then 2p1, 1s2, 2s2, 2p1. So, and then so you have to, so you have 2s orbital and then 2p orbital, okay, and it has 2 electron and it has 1 electrons. Then promotion of electron, promotion can give of this state, okay. So, there are 2 unpaired electrons. So, this is after promotion of electron, and then they combine and then hybridize to give 3 equivalent orbitals, okay, containing 1 electron each. So, it is called sp2 hybridized orbital, sp2 hybridized orbital, because 1 s orbital, that is s orbital, this is a 2 p orbital, 2 p orbital, 2 s orbital. So, 1 s orbital combining with 2 p orbital, so it is called sp2 orbital. So, there are 2 p orbitals are involved, that is why it is a sp2 orbital. They look like this. There is small lobe, there is another small lobe, this is positive, this is positive, this is positive, okay. So, this is for example x, okay, this is if you say this is z axis, this is y axis, okay. So, this can accept, so it contains 1 electron here, 1 electron here, 1 electron here, which can combine with another atom having 1 electrons. So, for example fluorine, okay, fluorine electronic configuration 1s2, 2s2, 2p5, 2p5, it has a 1 unpaired electron in the pz orbital, okay. So, there are, so this is a pz orbital contain 1 unpaired electron that can combine with the hybridized orbital of the boron atom and form a bond like this, positive negative, this is positive negative, this is positive negative. So, this is a boron like this, trigonal, okay, it is a planar geometry, okay, equilateral triangle, okay, the geometry shape of the molecule is equilateral triangle. That's how a bond formations happen. So now, okay, they have equal energy. These orbital hybridized orbital equal energy containing 1 electron, and the character is shared by s and p orbital. So it has a 1/3. It's a 2/3 of the p orbital. 1/3 of the s orbital and 2/3 of the p orbitals. Thank you.